Good afternoon, everyone, and thank you for attending our low layer count PCBs, Why They Are Not All Created Equal webinar. My name is Ryan Wood, the Content Marketing Manager here at Epic. Before we get started, I just want to let you all know that you'll be muted during the presentation. If you have any questions as we move along, please enter them into the questions panel, which is located in the webinar control panel, and we'll try to get to them all at the end of the presentation. If we don't have time to go through all of your questions, we will be sure to reply back to you by email. Also, we will be recording this webinar and we'll be posting both the recording and the slides on our website and YouTube channel. Our presenter today is Ed McMahon, the CEO here at Epic Engineered Technologies. And without further ado, I will pass it on over to Ed.
Thanks, Ryan. Good afternoon, everyone. And as Ryan said, my name is Ed McMahon. I'm the CEO here at Epic. And this year will mark the 23rd year since I first acquired my first printed circuit board shop back in 2001. So it's been a long journey, but it seems like in some ways we're kind of going back to a little bit of that, which is why we're going to be talking about low layer count PCBs here today. And why did we decide to talk about this topic? Well, what is not typically known is that low layer count PCBs are traditionally and still are the most used in everyday production, regardless of the fact that you heard, printed circuit board shops doing 20, 30, and 40 layer printed circuit boards. The majority of them are still 2 and 4 layer boards, and there's a lot of reasons for that, and we'll talk about that in a little bit. One of the other reasons that we decided to talk about this is since September, 5 printed circuit board shops have closed in North America, and almost all of them did lower technology product. And a lot of the reason that they closed was because they hadn't invested in technology, because even though 2 and 4 layer are considered lower technology, what we're going to talk about here today is that given the new technology on components and other things, these no longer can be considered low technology, and they're not as simple as they may have been in the past. The agenda's got some pretty specific things that we're going to talk about, but our goal here really is to be very specific around a whole bunch of design consideration, material selection, what you should be concerned about when picking someone to fabricate, and then looking at what the functionality versus cost is, because that really is what we're here to talk about today, right? Everybody wants to be able to keep their cost in control, but get more technology out of their end product, and we want to help them do that. So that's a big part of why we're doing this presentation today. And just to be to start off with a very simple thing, everybody knows what 2 and 4 layer boards are, right? What many people don't know is that the double-sided board was actually invented in the early 1940s, and it was about 20 years before multi-layer boards really came to fruition. You know, in the early 40s, right during the heart of World War II, is when the double-sided board really started to gain attention. So it's been a while since this technology's been out there. You know, again, we're getting close to 100 years of this product actually being available commercially. And we're talking about old school double-sided and 4-layer, right? I mean, it's interesting as you're looking at these two happen to be double-sided, right? Because you can see through them where there's no ground plane. But look at how little copper is actually on these parts, right? These parts were still being manufactured. We're still manufacturing these today for customers. But as you can see, right, you've got a whole lot of big lines and spaces. You got a whole lot of big holes that you can see all the way through. And this is traditionally what everybody would think about when you're talking about an old school 2 and 4 layer boards, right? And then you throw some components on that. And these two pictures aren't exactly perfect because there are some vias there, right? So you can see there's some new technologies on there, but the majority of the components on there are through-hole components. They're very big, right? If you, for the last 25 years, if you took apart one of your electronic components, this is what you would see, right? And regardless of what you did, you just have to put more of these components on PCBs to get the functionality that you want. And when you looked at old school 2 and 4 layer, the reality is that there were really only a couple things that you need to be concerned about when it comes to quality, right? And the first one would be the quality of a plated through hole, right? 4-layer, 2-layer boards. This picture here to the right is a 4-layer board, but you had big wide holes, right? And the whole idea was the quality of the plated through hole, which is not only the amount of copper in the hole, but the connection with the top layer and the inner layers. But it was kind of simple because the way that you get a quality plated through hole is in a plating bath that's getting fluid in and out of the hole. That's really simple when you've got big wide holes, right? It's just easy. You know, the actual panels are agitated in the bath, and it was really easy to get this kind of finish, which is exactly what you want for a through hole to look like. And the other big thing, right, was the quality of the etch circuit, right? The only thing you were concerned about back 15 years ago, even 5 years ago, really, was shorts and opens, right? You were just making sure that you didn't have any shorts or opens on your outer layer circuit, and you had plenty of space, right? Because if you go back a couple of slides ago, right, where you saw those traces, I mean, you could have ran that thing through the etcher 4 or 5 times and still been able to create a product that was in spec, right? So this is really the two things that we were concerned about back when, you know, 20 years ago when we were making old school 2 and 4 layer boards. And why was that the case? Well, because of cost or functionality, right? Nobody wanted their remote control to cost $500, which is why the remote controls even of today look like that picture to the left, right? You want to be able to sell that remote control for $5, and the only way you're going to be able to do that is by keeping cost out of the product. And using a double-sided printed circuit board is the way to do that. You didn't need any more. Could you build a remote control with a 10-layer board? You sure can. You could probably make it about, you know, a quarter of the size of that. But you don't want to pay $500 for that, which is why that functionality and cost equation works this way. On the right is really a single-sided board, but it's an LED aluminum board. And the reality is, because of the functionality, you really can't add any layers to it, right? So 2 and 4 layer boards have been used forever. And a lot of the time it was mostly by just the cost or the functionality that was the reason that made them different, right? And why you use them. And most people, when they decided that they had to go to things above 4 layer, was because mostly the functionality. So what changed, right? Well, specifically, right, what changed are component sizes, right? If you look back a couple of slides back at some of those resistors and capacitors and those other passive components that were through hole, they were pretty big, right? And then the whole surface mount revolution came, right? And then to the left, you saw how you were able to find surface mount passives that were pretty small, but yet they were still manageable, as that's a pair of needle nose pliers that are holding that there on the left. And then you get to today, right, where you got 01, 005 passives that you have to not only use a pair of very specialized tweezers if you're going to try to place them by hand, right, but you have to use a pretty substantial microscope to be even able to see, right? But that's what allowed all of a sudden 2 and 4 layer boards to create the functionality that a lot of customers needed. Along with that, you saw that the advent of a BGA or ICs with huge functionality and through holes with no components, otherwise known as vias, right? So you can take a BGA like that on the left, and what you're seeing is that these BGAs are attached to surface mount pads, but they have a via hole next to it that goes directly through the board and connects to layers 2, 3, and 4 if they needed it, if that's all the layers that were there. But because of these two technologies, all of a sudden you didn't need to have a lot of space on your PCB to get the functionality that you needed, and it's helping us in a lot of different ways. Because as you remember, those pictures on the left are what we used to have, and those pictures on the right are 2 and 4 layer printed circuit boards today. As you can see, you're putting a whole lot more functionality in the same exact space. Those 2 boards are the same exact size. And you can see the number of components that you're going to put on the ones to the left versus the ones to the right. And as you can see, there's very little through holes. I don't even think there are some plated through holes on the one on the right, but very few through holes, right? Because of the reality, you just don't need them anymore. because you've got vias connecting other layers and the components are all going on the surface. And remember that they're going on both sides, right? So not only do you have this on one side, but you have it on the other side as well. So you got a tremendous amount of room now to place all of those components. So everybody knows all about why we got to this point, but let's talk about the design considerations when you're talking about double-sided and four-layer boards with the new technology. And there's a couple of them, but we're going to focus really on three, right? The first one are fine lines and spaces, 4 mils and less. Really, 3 mil lines and spaces are the norm. And the reality, as you can see from this picture, those are really tight circuits, right? I mean, you're never going to see a short on any of those circuits unless you've got a microscope. But it requires a lot of technology to be able to manufacture printed circuit boards that can do fine lines and spaces that are that thin. Second one is very small holes, less than 10 mils, right? We're not talking yet about micro vias, 5 mils and less for laser drills, because we're talking about 2 and 4 layer parts, right? We're really talking about 10 mils and less, 8 and 6s, which are for the most part drilled mechanically, but they're a lot different. Remember, we talked about the big holes in the old school double-sided board, and it was really easy when you were trying to move fluid through a 20 mil or greater hole. Now think about trying to move fluid through an 8 mil drill hole. It becomes a whole lot more difficult to create the quality that you're going to want from those through holes. And the last thing we'll talk about are what we'll call solder mask dams as small as 4 or 5 mils. When you look at a BGA like the one in the middle of the picture, or if you look to those quad packs to the right, you could get down to 5 or 4 mils between those individual components. And it's really difficult to be able to get adhesion with that little amount of space. And along with that, there's registration that goes along with it as well, right? It's just not being able to get that solder mask to stick, but you got to be able to make sure that you're not putting it on the pad, when you're imaging off that particular image. So how do these design considerations affect cost, right? Well, first of all, every single one of those things that we talked about requires specialized equipment, right? And they have a really high effect on yield, right? When you look at the over-etched PCB to the right, if you look at a 15 mil trace, for example, right, and you talk about the IPC specification, which are plus or minus 10%, that means you get 1.5 mils on each. You get 1.5 mils in terms of your, if you go under, if you over etch the circuit versus not even 0.5 mil on those smaller traces. In all honesty, with some traces that are 3 and 4 mils, if you have that thing in your etcher for 4 or 5 seconds extra, it's going to be gone, right? And there's no way to get it back, right? When we started this back 25 years ago, and you had a trace that somehow got etched off, I mean, we used to, back in the day, we used to actually weld circuits together to be able to, to keep yield up. You can't do that anymore, right? And not only does it add, if we talked about high effect on yield, and why does it add time? Because you have to be dialed in, right? As a printed circuit board manufacturer, on my etcher, for example, I'm going to run, hundreds of panels a day through that etcher. And if I'm depending upon what I'm running right before this, my etcher is going to have to be dialed in for this technology before I start. It's just not putting it in one side and putting it around the other. I mean, we've seen that, at some points you could be, etching 4-ounce copper 5 minutes before you want to throw a 3 mil line and space job in there, and you're halfway down the etcher and the whole image is gone, right? So it takes a lot of time to process, and it adds cost to the product. So a double-sided board like my first showed is not the same cost as a double-sided board that you'll see that we're talking about now, but it's also not as expensive as an 8-layer board. So there's benefits to everything. A couple of ways to talk about how we manage cost on these double-sided parts, right? There's a couple of things that are specific, right? One of them that we see a lot, especially when it comes to vias on double-sided and 4-layer boards, is making sure that you identify the way you want your vias treated, right? Because a lot of times, you know, if VIA's not covered, that second one, that was usually how VIAs just were, right? And then you've got everything from just the solder mask tent, which is basically just having a layer between in the sides of the hole. And depending upon the size of the hole, if you've got an 8 mil hole, that's not hard to do, right? Because that material will absolutely image and develop over the top of that. A plug via is a little bit harder. It's actually a specific process. You know, it's not as easy in many instances as just saying, well, we're just going to plug that via with solder mask. Sure, but it requires a specialized process. It's not just you use your standard screen printing process to try to push the material down through the via. What happens if you do that and you don't have vacuum or you don't have a mechanism by which you're checking that is you'll get a void inside of that via. And what a void means inside of a via that's plugged with solder mask is you're going to get outgassing when you heat it up. And you're not going to find out about that until you run that through an oven or any other process for soldering. And then there's active pad, which is, you know, you can fill these vias with conductive, non-conductive product, and you can actually plate over the top of it to keep an active pad. So the key is to make sure that you identify what you really need for your via. Do you really need a plug via? Why is that, right? You may not, right? But if you could get away with just a tented via, all of a sudden you're keeping your cost down. The second thing to keep in mind is making sure you always use the largest features possible. That means your holes and your traces and spaces. And not only is it distance away from other features, including the edge of the board. Just because you can use 3 mil lines and spaces doesn't mean you have to, right? And especially doesn't mean you have to the entire way. Right? If you've got a situation whereby, you know, you've got some features that you need to get through a certain area to what you want, absolutely. But it doesn't mean you have to do it on the whole entire part. And then lastly is making sure you work with your fabricator to DFM your BGA designs. There's an awful lot of calculations that go into how we can manage a BGA from a manufacturing perspective. And the way that we can help you is to help you before you finalize your design to make sure that if one of those 8 specific measurements aren't met, we can help space things out so that they are, right? And it's not just, oh, I just need to keep 3 mils between my features. It's not that simple, right? So that's why we want to help you as our customer while you're doing your design to make sure that we give you the best chance of being successful, especially, you know, with these BGAs that could be, you know, any number of pins, and they're getting more and more as technology increases. So when we talk about material selection for 2 and 4 layer print circuit boards, it used to be with 2 and 4 layers because they had so many through-hole components was that you wanted to use the highest TG material that you could. Now, TG material, let's go back and talk about what TG is. TG stands for the glass transition temperature of the laminate, which means that that is the temperature by which the material will deteriorate. And 99 times out of 100, the material is deteriorating, not because it's seeing an operating temperature of that. It's usually deteriorating because of assembly or because of rework, right? If you look at that picture there, right, traditionally with double-sided that were through-hole components, you used a soldering iron to solder specific components to the board. In this particular case, that's what this is showing. Now, when you look at a big honking toroid or a big honking heat sink or other product like that you're trying to solder to a board, you have got to use a substantial amount of heat in a very small space to get the solder to flow to actually solder the part. And that creates a challenge. And that's when you really need to make sure that you have the right TG material selected, because that's when it's really going to matter, is when you're trying to either add a component like this and you have to do it by hand, or if you're going to rework components based upon your application. When you look at newer designs and these 2 and 4 layer printed circuit boards, right, you have to ask yourself, are you going to really rework these? Well, The answer is that you can, and a lot of people do. Now, when you talk about taking things off like that BGA far to the left, there's a specialized piece of equipment that you're going to use to do that, right? And that's just built because those components are so expensive. And if you look at some of those really small components that are going to go on there, the amount of heat you're going to need to get those off to rework them is really minimal, right? And that's the point, right? And that's how you can take some cost out of your end product, is because you really don't need that level of protection if you're going to be just removing surface mount parts. And in all honesty, in many instances, what ends up happening is that the customers take off their high dollar parts and just let everything else go. But if you needed to rework something at the assembly level, sure, you're going to want to make sure that you can rework these, but you can do it with a TG that is lower. If you look at that board in the middle, you're going to see some through holes that are over to the left that are isolated, that aren't near anything else. Why is that? Because you're going to solder flow way easier because you don't have any heat sink that is going to take the heat away from what you're doing, right? So there's a lot of little tricks to the trade, but that's really why we talk about when you need higher TG material, is what your application is going to be. And in all honesty, where it matters the most is when you have large components that you're going to need to regularly replace. I would say 10 years ago, even with the advent of selective soldering equipment, where it used to be that you would put through-hole components through and you'd run it through a wave solder. Well, I would submit to you that now that 80% of all the components like this on a mixed technology board are being soldered by a CNC controlled selective soldering piece of equipment. So at the original assembly, you're going to be able to really control the temperature and the amount of time that you're going to need when you're putting these together, right? You're going to be able to do it very, very accurately. However, if you have a situation, for example, we have one customer who, let's say they had these, 3 big transistors here, and typically that's the thing that either ran out of shelf life or either broke in their application, but the rest of the board was fine. In many instances, they will replace the board at the customer level, bring the board back, and want to replace the one component to keep using that particular board. If that's what you're going to do, you're going to want to really think about having a higher TG material, because you're going to have to apply some heat by hand to remove that component and then put it back on. And that's where the biggest risk when it comes to material is for 2 and 4 layer designs. As far as impedance control on RF circuits on 2 and 4 layer, you can absolutely use these technologies to have this kind of control. Now, there's a couple of things that we see often from an impedance control perspective that you need to be aware of, right? And the most important thing is around keeping your impedance features away from soldered features, right? Typically, because you're putting it on a 2-layer, an outer layer, you've got all kinds of space. You don't think about the fact that I need to keep the impedance feature away from the soldered feature because I got plenty of space, right? So if you look at the top right, one of the things that we'll design for manufacturer look for our customers is making sure that you're keeping a 10 mil minimum area between the impedance feature and the soldered component. Because if you don't, what you basically do is you create a heat sink, right? And if you try to solder that component, what you will do is that the left side's solder pad will get hotter than the right side, and you could find yourself with a tombstoning challenge, which is something that is difficult to find until you're in operation. So that's the one thing about impedance with double-sided and 4-layer boards you want to keep in mind. And then the bottom picture is where a customer, because he had so much space and because we can keep the line so thin, you can now find yourself creating the desired impedance you want using a non-standard image, right? You don't usually see images like this where you're creating more impedance by creating more space or more copper between the component and what you're and where you're trying to go with it. But that's possible, and it's used more than you would recognize on 2 and 4 layer boards today. So let's talk about manufacturing 2 and 4 layer boards, right? Because they're really not all the same. You know, back 15 years ago when they were through holes, they were big wide holes and big wide traces, you could totally do it. But today, with tight spaces, with less than 10 mil holes and 5 mil dams, it's a big difference, right? That piece of equipment at the top is a UV exposure machine, and that's what was used for so many years to not only expose images of circuits, but the solder mask image as well. And unfortunately, a lot of factories today still use that as their primary mechanism to image both of those. The challenge with that is that how you use one of these pieces of equipment is that you use a piece of film. And that piece of film is registered using a pin on the top and a pin on the bottom, right? And then you run it through and it goes in and UV light exposes everything, it comes back out. It's a very manual process and it's very difficult to keep registration tight, especially when you've got tight features, right? What you're looking at down the bottom is a laser direct imaging machine. They come anywhere from, 1 up to 4, maybe more now, lasers to actually create the image, not only of the circuitry, but of mask, right? And that's what you really need to be able to not only manage the registration, but the quality of the traces. The difference being is that those OLED machines up at the top, you could probably pick up for $2,400 right now. Those laser direct imaging equipment down the bottom can run you, $450,000 for a 2 laser, up to $700 for a 4, right? So that's why that investment in equipment is so important when you're doing 2 and 4 layer boards. When we talk about the solder mask challenges, right? You talk about the difference between using that top piece of equipment and using the bottom. The reality is that if you look at that picture to the right, what you're seeing is that you're trying to hold 4 mil dams, which you're trying to adhere 4 mils of solder mask between those dams for that quad pack. Well, using that UV machine, not only is it very difficult to do, but it's very difficult to keep the registration tight. You look at that picture, you can see the gold areas where a lot of that material is gone, but if you look at the top, you're seeing where the registration is difficult. It's very difficult to manage registration with film and UV. There's not enough targets. Every single panel is different, and you're just trying to go after the averages when you're using UV, where that LDI machine registers every single panel to targets. So no matter what happened during processing, you have a much better chance of managing registration. And this is what happens in terms of, to the left is it's what's called a tape test, right? You basically have to put a piece of Scotch tape over a feature. When you pull it off, this is what it ends up looking like. So over to the right is a solder mask dam. Over to the left is when you don't have good exposure of your image on your solder mask. This is what ends up happening. The other real thing to talk about is your drills and your through holes, right? And your vias, your very small holes that aren't going to have components but go from top to bottom, right? The old way, that Mark 6 drill that everybody had at one time or another, right? You have tooling holes in a panel that you use for everything, right? Those tooling holes are used all throughout the process. They're putting on and taking off of those tooling holes 20 times. So you can imagine how much slop you get into as you're, going through the process. To the right, or to the bottom, I'm sorry, are drills that are basically using cameras to identify features on every single, not only panel, but even sometimes features within the panel, right? So this helps us make sure that even with those smaller holes, we're improving our yield and we're getting our registration right every time, because that's what's the most important when you're talking about small holes, because all you have to do, if you're talking about an 18 by 24 panel, which is most of what we use in the US, from corner to corner, that's a lot of distance, right? And with that Mark 6 drill, you could literally be dead nuts on at the top left-hand side of that panel. By the time you get to the bottom right, you could be off by 4 or 5 mils, right? And you got half the panel is scrapped, and you won't even know it until you get to the next step. right? So for us, that's why having that investment in these bigger drills is the way that we keep our costs down, because we can get our yield to where we need it to be. And then even small things, right? What we're seeing now is with silkscreen, right? Silkscreen Legend used to be screened on through an image that was made on a screen, the same as a t-shirt is. And that process is still relatively common today. But the top of that is all of the processes that have to go into making the screen, screening the product, and then it doesn't even talk about the fact that you have to actually clean the screen when you're done. Versus what's inkjet Legend printing today, which is the Sprint 120, which is one of the ones that we have at our facility. But it's not only a faster and consistent process, it can print much finer lines. And along with that, it's got more functionality, right? I can print QR codes, I can print serial numbers, I can put all kinds of data on every individual piece, along with the fact that I can print traceability stuff on my panel so that I have a better understanding of what my process is doing as we move it through the shop. And this is an investment that's required, even with those 2 and 4 layer printed circuit boards. The cost versus functionality argument is always one that we make with customers, right? And like we talked about earlier, the #1 rule of thumb: always make things as big as you can, right? It improves the long-term reliability. It's going to reduce your cost, believe it or not, because it doesn't matter if you've got a printed circuit board that's got 80% of the product of the surface is still copper feature, or 10%. The process is still the same for us. So if you make things as big as you can, that's helpful. And there's more room for error. Like we talked about the fact that if you've got a 20 mil trace and you got plus or minus 10%, I got 2 mils to be able to play with and stay inside of IPC spec, versus a 4 mil trace, I only got less than a half a mil. And it gives me better yield and it helps me keep my costs down, right? But if the features need to be small and the tolerances are tight, that's okay too. Just make sure that you're working with the right fabricator, so that you're making sure that they have the right the right equipment to give you what it is that you're looking for. So what's next for 2 and 4 layer? Well, the features are going to be getting smaller and smaller and smaller, right? And you're even starting to see some applications where we're actually going to be mixing subtractive and additive technologies into printed circuit boards, which is going to be pretty exciting over the next 5 years or so. But if you look at that board to the top, that's a 4-layer board, right? That's a 4-layer board with some RF material and some really, really difficult castellated edges on the side that are basically an IC substrate chip. Because semiconductors are going to be getting more functionality, right? And because of that, the semiconductor is going to do a lot of the heavy lifting in terms of the functionality for our customers' devices, which means they're not going to need to put as much many components on, because that IC is going to do a lot of it. Additional to technology from a processing perspective will need to be required. And as we've talked about to this point, fabricators are going to have to invest, right? If we're not continuing to invest, we're really going to struggle to keep up with what our customers need, because things aren't getting bigger, they're getting smaller, and you just can't do it with old school equipment, which is a big part of the reason that many of the fabricators that we talked about went out of business since last year. If you look at that board, down at the bottom there, that's got plated through cavities in there, having even plating tanks. Plating is an old school technology, but at our facility in Dallas, we've got 4 different types of copper plating depending upon what it is we're plating. That's a pretty substantial investment when you're talking about being able to give the customer what it is they want from a high technology perspective. So summarize it off, right? Not all 4 and 2 layer PCBs are created equal. The feature sizes are not going to get bigger, right? And not everybody has made the investment to keep up with it. A lot of people have, right? Unfortunately, many of the people that have made that investment aren't in this country. And that's part of the reason why, Asia is really one of the places for a lot of the high-tech boards today. And it's why people like Apple get a lot of their stuff from facilities in Asia, because they made the investment. A lot of us in the U.S. have, and a lot of us in the U.S. will continue, but a lot of it, that investment is gone over in Asia. And again, every fabricator in the U.S. has a DFM service. Every fabricator would tell you in a heartbeat that they would love to see your designs 4 or 5 times before you submitted it for manufacture, because it's going to make their life easier. There's not one manufacturer in this country that doesn't want to help and that wouldn't rather have you send them Gerber files once a week and say, hey, run this through to make sure that I'm on the right track so that you don't have any problems when you finally get to manufacturing. You're under the gun and you're not going to have the time to make changes. So please use that service. And I don't care who your fabricator is, all of them want to be able to do that. All right. So that's enough for the battery thing. I'm going to go, or excuse me, for the PCB stuff. I'm going to go ahead and look at the questions, but real quick, just some of the other products that we do. As many of you know, we started 50 plus years or 70 plus years ago making printed circuit boards, but we make a lot of other products today, all for the electronics industry, all of them that are really PCB based. And we're proud of the fact that we've been able to move out into other products as we move forward to help our customers. So I'll let Ryan go over this while I'm looking at some of the questions.
Thanks, Ed. I just want to take a moment to mention Instant PCB Quote, our in-house quoting and ordering tool for PCBs. What many people don't realize is that you can quote and order PCBs online up to 16 layers. From prototypes, pre-production, and production volumes, we have many options available that can be done online. If you're not already an Instant PCB Quote user, simply go to epictech.com/Instant PCB Quote to get started and create your free user account. Now I'll turn it back over to Ed to go through some of the questions that came in.
Great. I'm going to pick 3 here. First one is, what is the best way to determine if a fabricator is capable of doing what you need? So that's kind of a trick question, right? Because unfortunately, someone just sends you samples of what it is they of similar designs. Real difficult, right? Because it's awfully hard to know where that's manufactured. Traditionally, a site visit is probably the best. But if you can't do that, pictures of what they have for equipment, because that's really going to tell you what you want to know, right? If they have LDI, if they have the right shows, you're going to be able to see that, right? And you'll be able to understand if, in fact, they've made it, because a lot of companies, too often or not, they use that maybe lower technology equipment to try to make the high technology stuff. And what they do is their yield's only 30%, but they don't, that's just part of what they do. They just make a whole lot of it and try to inspect their way to quality. So that's probably the best way to do it. The next question was, how do you measure for over etching as it will pass electrical test? That's very true, right? If you've got a 5 mil trace and it gets over etched and it's down to 2.5, it's still going to pass test. Now, there's a couple things you can do. I mean, you can obviously do some sort of a high pot test where it wouldn't pass, but the more effective way to do that is what we see from some of our customers, and we recommend, is if there's an area you're concerned about on your board, as part of your submission of your purchase order, we take that image of the board and circle the area that you would like measured. And the factories like us, we have microscopes that we're able to measure with a computer the area that you want, and say that you want 5 of these printed circuit boards tested, and you want the picture and you want the measurement to make sure that all of those areas are etched the correct amount. And that's fine. Again, that's one way to do it. Make sure they pick out 5 of them. Again, it's really hard to do unless you have the computerized equipment. You can do it obviously under a microscope, but if you're talking 3 and 4 mil lines and spaces, you can do it you can see with a loupe, but it's really hard to measure when they're that small. And the last one was, how do you specify if you want serial numbers or QR codes based on your PCBs? Well, there's a couple of ways to do that. One is that we have some customers that just give us a standard of what they want on everything, and we just use that, and then we put that on their boards as we manufacture, and they have a whole serialization scheme that they use, so they give that to us. Others, they just do it by actual board. So you can put a serial number on it that's got date code, part number, a whole lot of other stuff. But really work with your fabricator because it's not that difficult to do. And once you come up with a scheme with each other, it makes it pretty easy. And our engineering team is comfortable with adding it on as we go forward. So work with your fabricator. All of them are capable if they have the right technology of doing that. So what we'll do is we'll put the rest of these questions on the web. We'll send out an email with all the questions being answered. We appreciate everybody taking the time today. Thank you again for coming by, and we look forward to having you on many more of our webinars because we try to do 4 to 5 a year. So please look out for the next one. Thanks, everybody.